Is it true that any even integer to the power of any even integer is always going to be even? Well, let's think about this, right? Well, what are our even integers that we can be considering here? Well, the first things people think of are 2, 4, 6, 8, right? So let's give those a shot first. Let's do 2 to the power of 2. Let's try maybe 2 to the power of 4 as well, right? So 2 to the power of 2 is going to be 4. 2 to the power of 4 is going to be 16. We can try 4 to the power of 2 and 4 to the power of 4. That's going to be 16. And then this is going to be 16 times 4 is going to be 100. No, it's going to be 64. And then 64 times 4 is going to be 256. Okay, so that seems to be holding true for the statement. But something people forget is, well, 0 is also an even integer, and so is -1, -2, -4, and so forth, right? So we should also be trying 0 and the negative powers. So let's give those a shot. Let's try that as well. Let's try 2 to the power of 0, 4 to the power of 0, 6 to the power of 0. Well, what do we know about all of these? These are going to be equal to 1, right? Any number to the power of 0 is going to be equal to 1. Okay, that already shows the statement's not true, right? These are two even numbers, one to the power of the other, and the answer is not even, it's odd. 1 is an odd integer. Okay, this is already more than enough proof to start writing the proof for why this is false, but let's just be a little more thorough. Let's try the negative numbers too, right? Let's try 2 to the power of -2 and 4 to the power of -4 maybe. What is this going to be equal to? Well, this is just going to be equal to 1 over 2 squared, or 1 over 4. And this is going to equal to 1 over 4 to the power of 4, which is going to equal to 1 over 256, I think. But the point is that when you do the negative numbers, you get fractions. And fractions cannot be even numbers because even numbers have to be integers. And fractions are not integers, right? So there we go. We can already see that for 0 and any even power that's 0 or less, this statement will not be holding true. So it's not true that for all even numbers to the power of all even numbers, they're going to be even. So that means that this statement is very clearly going to be false. But how do we prove this? Well, the very first thing we should do is write out the actual statement we originally asked, right? The original question we asked is for all a and b, and we're going to call this a and this b, for all a and b that are integers, if a and b are even, then a to the power of b is even, right? And this statement that we made, we know is false. So how do we prove a false statement? Well, we write out its negation, and then we prove the negation must be true. So what is the negation of this statement? The negation of a for all statement is going to be that there exist a and b that are integers where a and b are even, but this but is super important to write in your negations. A to the power of b is not even. Why am I saying not even instead of odd? Because usually when you think of, well, if it can't be even, it must be odd. Well, in the examples I showed, okay, there are examples where it's odd, right? There are examples where 2 to the power of 0, 4 to the power of 0 is going to give you an odd number. It's going to give you 1. But what about the negative powers that we chose, right? The negative powers we chose for b, these were not integers, right? They were not integers, which means that they could not be even, but it also means they couldn't have been odd. Odd numbers also have to be integers. So that's why we're just going to say not even. You could say odd as well, but this is a better statement to make, purely because it covers all of the cases that can negate this. So what do we say? To prove a there exists statement, you can just give an example of a and b where this statement is true. You're just saying that there exists some. So give them one that does exist. Give them a pair that shows this is true. So we say, for example, or let's make this a sentence. Let a and b be integers. Maybe you can just immediately jump to assigning a and b to be some numbers, but we're just going to be a little bit more explicit here. We're going to say let a and b be integers such that a is going to equal to 2 and b is going to equal to 0. Then a to the power of b is going to be 2 to the power of 0, which is just going to be 1, and 1 is not even. Now here you can immediately jump to saying that the negation is true, so this statement must be false, but I'm going to actually prove 1 is not even by showing that 1 cannot fit the definition of even. So we're going to say because, or let's write that as a separate sentence, 1 is not even because if 1 equals 2 times k plus 1, or sorry, 2 times k for some k that's an integer, I'm going to put in brackets definition of even. This is kind of a proof by contradiction. We're actually assuming 1 is even, and then we're going to write it that when it is even, it doesn't fit the definition of even. So by contradiction, 1 cannot be supposed to be even, and then shown it's not even. But so this is kind of an informal part of a proof by contradiction. But what we say is then k must be equal to 1/2, right? If you rearrange this for k, and 1/2 is not an integer, so k is not an integer. So by contradiction, 1 is not even. Fantastic. This means, so now we can write our concluding statement. This means the negation is true, so the original statement is false. Fantastic. You can also, instead of using this example, because we just need to show there is an example, right? So you could have written this as odd, but if you want to use negatives, you would then just need to prove the negative is a fraction, and that's also not going to give you a k that's an integer, which it must be by definition of even. But fantastic, we've now disproven that an even integer to the power of any even integer is not always going to be even, because when it's to the power of 0 or any negative even number, it's going to give you either a fraction or an odd number.